Hi, I'm Slava. We've heard some really amazing talks. I don't want to undersell my own, but it's not going to be exactly earth-shattering stuff. However, it's actually really important to talk about because without a well-designed and well-configured client, you're not going to get all the performance out of Valkey that you can, and you're not going to keep it operationally stable without a well-behaving client either. First, a little bit about myself. I'm a member of the core services team at Nextdoor. I've been at the company for 10 years, and I've seen and participated in the various evolutions of our caching infrastructure over the years. Outside of work, I enjoy Formula One, cycling, and sim racing. So here's our agenda. My goal is for you to walk away with a deeper understanding of different client behaviors and implementations and what to look out for, because not all RESP clients are created equal. All right, we've heard a lot about fork-based stuff. One more thing, our application uses fork-based serving and processing. If you're not super familiar with that, you have a master process that spins up and creates fork worker processes. Those do things like serving your web requests. Caveat with this is you can't safely share TCP connections across your workers, which means that there's no ability to do connection pooling. Your connections churn as workers go through their life cycle. And you can wind up with thundering herds as a bunch of workers spin up and all go try to talk to the cache. So here are the feature sets that we wanted. We wanted automatic pipelining, latency-aware routing, circuit breaking, better timeout handling, and in-process cache, and some nice-to-haves were dynamic configuration and better observability in general. So for context, we run in Kubernetes. We have our application pods. They have a number of processes. We run our daemon, or our proxy as a daemon, so all of the processes on the node talk through the daemon to talk to Valkey. This drastically reduces the number of connections that we have. And why is this important? I think we've previously heard this. While Valkey can support 65,000 connections, what happens when there's a network hiccup and everything pauses for a second, requests queue up, and then they go? The answer is nothing really good. Centralizing through a daemon allows us to centralize the circuit breaking as well. So that's a benefit there. So we're done talking about some context. Let's talk about generic aspects of RESP clients. First is how do they handle commands and connections? There are 4 patterns. The first one, this is kind of the most naive one, is connection pinning. You have a set of connections in a pool. When a worker or application wants to communicate, for each command, it goes and checks out a connection. And if there's not enough connections to fill the requests, things are blocked. Next is pipelining. Here we have application code that actually performs some sort of batching in terms of the commands that it sends. So for instance, get key 1 and get key 2. With this approach, you can get economies of scale around buffers, packets, L2 caches, etc. But let's face it, not all applications are written in this way. So next is automatic pipelining with batching. Here we have worker A and worker B. They each want to get a key from the cache. They send their request to the pipeliner batches them up, sends it to Valkey, waits for a response, and then sends back the appropriate response to each worker. The common implementation of this is as soon as the first request is received, there's a clock that starts, waits to fill the batch, and waits for the clock to run out, and potentially there's a byte size limit for the batch or number of commands. The previous example, the workers were blocked until the entire response was received. In streaming, we decouple reading and writing. So it means, first of all, you can have multiple in-flight pipelines going, and you can read as you go. It's still sequential, but it means that worker A can get value 1 back as soon as possible, as soon as it's serialized or deserialized. Now, this seems like the most obvious thing that you want, but many applications are pigeonholed into what is essentially connection pinning. So let's talk about routing next. How does a client pick which shard node to communicate with? The most naive approach is writes go to the primary, reads go to the replica or replicas. A variant of this might be that is to send everything to the primary and your replicas act as hot standbys. Another option, which we've heard previously, is to send your read requests to the same availability zone as your client. The benefits of this is that it's much lower latency, and if you're a cloud provider, the network cost is much cheaper because you're not paying for the cross-zone network transfer, which can be more expensive than the cluster you're actually operating. So the third option, and this is the one I recommend, is latency aware. It behaves similar in practice to AZ aware, but is more flexible in terms of routing around network problems or hotspots even. It can be easier to implement on the client side because your clients don't need to know which availability zone that they're in and which availability zone different nodes are in. And on the implementation side, you can just measure the request times that are already flowing or just periodically send a ping command, which is an actual Valkey command, and just measure the timing of that. Now, that has the benefit of giving information of how loaded the server is. You can technically use a network ping, but then you don't get the load information. All right, next, let's talk about backpressure mechanisms. The most common one is backoff and retry. This is typically on a per command basis, but you can wind up with connection storms or retry storms with enough clients connected if they're not configured very well. Now, location of the retry really matters, right? Ideally, you want it to be before any of the routing decisions. I want to reiterate that, before the routing decisions, because you don't want to retry on a node that just gave you an error of like, hey, I'm still loading, right? The other option is circuit breaking. This is the one that I recommend. It's a little bit more flexible. Basically, your connection can be in one of three states. It allows all requests, it allows some requests, or it doesn't allow any of the requests. And you have a few reasons that can trip states, for instance, timeouts or number of errors, that sort of thing. The devil is in the details on the ramp-up phase and the tuning of it, but this can really effectively prevent connection and retry storms on the clients. So we need to also talk about timing out and configuring that because it's fundamentally linked with backpressure. It's really important to understand how timeouts are configured, handled, and propagated within your application. For instance, are request timeouts and TCP timeouts linked? So your application says, hey, I want this request in 10 milliseconds. Well, what if the TCP timeout is 100 milliseconds? Does your application wait? Right? You need to know this because this will really determine your failure scenario on the application side. Last thing to consider is how are partial successes propagated, right? Let's say you have a pipeline that the application sends. Does it get a error response for the entire thing? Are there partial successes? Do you know? It's really important to know and test this. All right, let's talk about some of the less apparent aspects of a client. This starts getting into the high performance realm. The most frequent thing that a client library is going to be doing is converting to and from the RESP protocol. This needs to be as efficient as possible. So it really matters how the requests and responses are processed. Is it in a batch, right? Do we wait for all the things to come back to Valkey before we start processing them, or can we do it in a stream? This really matters if you're in a language that has a garbage collection, because allocating and holding onto memory is not free. And even if you're in a language that doesn't have it, it's still pretty important. So next up is context switching. There's different types of context switching, but fundamentally all pause work to go do something else. The thing to ask is, how does my client work under the hood? There's two options. There's a native implementation. Let's say it's in the language that you're in, of like it's written in Java and you're in Java. It can use green threads, coroutines, or OS threads to actually do work and communicate with the cluster. All of these have context switches. It's not a problem, right, that they actually use these things. It's using them efficiently and effectively that's key. The other option is that maybe it's written in a single language like Rust and then has cross-language bindings. When you're jumping between two languages in an application, that context switch is usually pretty expensive, which is not necessarily a problem, right? But you don't want to put this in a hot loop, for instance. That's going to kill your performance. Last thing to mention is around how's networking handled, right? Is it select? Is it ePOL? Is it IO ring, right? All of these have different profiles in terms of context switching and overhead. All right, last thing is contention. Contention comes in many places, stats, queues, random number generation, and scheduling. The first three are around mutex, shared mutexes. And spoiler, if you're on a machine with lots of cores and your application uses all of those cores, this is going to get really expensive in terms of time spent. The last one, scheduling, it's a prominent issue in Golang, but variations of scheduling problems exist in all other languages. And all of this stuff can kill your performance of your application when communicating with cache. And the last thing I wanted to mention is that all of your problems, not just contention, they all get worse as your cluster scales in size, right? A client needs to have more context switches, allocating more memory, have more connections. All of this kind of backpressure goes back to the clients when your cluster grows in size. All right, a few parting thoughts. First, lessons learned. So we decided to write the proxy in Golang. It was not a bad fit. I wouldn't say it was a great fit either. A lot of the technical complexities around the project was around really efficient memory reuse, allocation, and just what I describe as generally fighting the garbage collector. Also, Go routine scheduling on busy machines was fun to kind of debug and understand what's going on there as well. The last thing I'll mention is that operating as a daemon for us is the right choice, but it's a little bit tricky because of the diversity of hardware and load profiles in our Kubernetes cluster, right? And that winds up into kind of manifests in different ways on our application side when that happens, when the proxy is slow, for instance. OK, I have only one takeaway for everyone, and it is, does my RESP client fit my use case? Because I don't want anyone to go home or go back to work and start replacing your clients. That's not the point of this. Use this as a jumping off point to evaluate your configuration of your existing client, do some performance benchmarking, and go from there. And if you have to pick a new client, redo those two things. And then whatever you choose, keep your clients up to date. That's kind of really important, right? Because they will improve and they'll get more features that Valkey has to offer.